should be part 3. We did these measurements on the earlier video. We're now going to take this and let's tidy this up here a little bit with some scale measurements. We're going to use 1 centimeter is equal to 1 Newton. I think we were using that before.
So we're going to measure 6.6 centimeters. Along our line. Remember, the tip of the arrow should not extend your line, so draw from the tip of your line backwards to make your arrow. So that's 6.6. The angle, by the way, is measured to be 6 degrees. I maybe did that off camera. These, I've got a couple different kinds of protractors available in the room. These don't seem to be as well made. So I would go with these semicircular protractors. They seem to be a little bit more precise in the alignment of these axes. So anyway, from here we are 6 degrees out. And we'll go ahead and measure this one while we're down here. So get that lined up. Be real precise. Any small mistakes here can kind of add up. So this is 10, 25, 27.5. So we're at 27.5. I've already jotted that down. The magnitude, that's the direction of course, the magnitude of this force is 8.1. So we'll get this lined up carefully. Come out here 8.1 centimeters. And there's our arrow. Okay, so, and then we've got this one over here to the right. When I lined up this piece of paper on the force table, underneath the spring scales, I intentionally made this force along the line. Now it's off by probably about a half a degree when you look way out here, but I'm going to go ahead and kind of keep it simple here. It's 4.3 newtons off in that direction, so. All
right, so next we're going to break this up into components. This is where we're using our sine and cosine functions. So here's some equations you'd already be familiar with. I just clipped these off of an equation sheet that we'll be using. So let's start, first of all, let's start with the easy one. Then we'll call this F1, and we'll call this one F2, and we'll call this one F3, force 1, force 2, force 3. F1 is entirely in the x direction, so if we were to break this up into x and y components, we really have no work to do. F1 little subscript x is the entire 4.3 newtons. F1y is equal to 0 newtons. X is this direction, and it's all in this direction. In fact, it is when we consider the fact that it's to the left, it is a negative 4.3 newtons. Now, the spring scale can't tell you negative forces. We have to make that call based on the orientation, the direction of it, and what we define as positive and negative. And we define positive this way and negative that way. Positive to the top of our page, negative to the bottom of our page. So let's move to F2. So we've got a tall, skinny triangle here. And we're going to break this up into the x and y components. Now we could do this by measurement and measure this to be about 0.6 centimeters, which means it should be about 0.6 newtons. But what we're going to do is break this up into x and y components and use our trig functions. So this leg of the, when we break this force up into a y component and an x component, here's our y component, F1y. Here's our x component, F1x. We use our sine and our cosine functions. So I'll do this one over here. So for F1x, we're going to use the sine theta equals opposite over hypotenuse. We are solving for the opposite leg, opposite to this angle. And so when we rearrange this, that opposite leg is equal to the hypotenuse times the sine of theta. We know the hypotenuse. The hypotenuse is this 6.6 newtons. And we know the angle, sine of 6 degrees. And so now we use our calculator to get a numerical value for that. So we have 6.6 sine of 6, and that is 0.69 newtons. And so my measurement was around 0.6, and this is the calculations telling us about 0.69. So Not bad. That's pretty close, especially for such a skinny little angle. All right, let's do the one over here, F1y. And in this case, we're going to use this is the adjacent leg. So that is the cosine function. So the cosine of theta is equal to the adjacent leg over the hypotenuse. And we're solving for the adjacent leg. So the adjacent leg is equal to the hypotenuse times cosine of theta. We know the hypotenuse, it's at 6.6 we just used, newtons. Notice I'm including the units to kind of carry that through. And cosine of 6 degrees. So 6.6 cosine of 6 degrees is 6.56. Notice in terms of common sense answers that this hypotenuse is 6.6 and this is almost that entire length, and that makes sense because these two arrows are almost the same length. This one's a little bit longer because of its angle. In terms of directions, this one is up and that is positive, so I'm going to indicate that with a positive sign, meaning, indicating I've thought about that. This is, it's to the right, so it's positive. This is up, so it's positive. 6.56 newtons. All right, down here to F3. So this time we've got a little bit bigger triangle. And actually, if you want to do this with measurement, that should be a nice perpendicular line. So I'm going to go ahead and make sure that I'm squared up here as I do this horizontal. There we go. Now, if I measure that, I'm measuring about 3.8. So I'm going to jot that down for a second. That's about 3.8 centimeters, which means it's about 3.8 newtons. We'll see how the calculation kind of works out. And if I measure this vertical one here, I'm at about 7.2 newtons. So we'll see how those two pan out. All right, this is 27.5. We measured that earlier, is our angle. So let's do our opposite leg over here. So the opposite leg is equal to the hypotenuse times the sine of our angle theta. Our hypotenuse down here is 8.1 newtons. Sine of 27.5 degrees. So 8.1 sine of 27.5. It's 3.74 newtons. And it's in the positive x direction, positive 3.74 newtons. And then for the y component down here, I'll move it down just a little bit so as to not get too close over here. We've got the adjacent leg is equal to the hypotenuse times the cosine of theta. That was the same equation that we applied up here. Hypotenuse down here is 8.1 newtons. Cosine of our angle here, 27.5 degrees. So we have 8.1 cosine 27.5. That is 7.18 newtons. Notice in this case, however, that this vector is representing this length. It is in the negative y direction, so that's negative 7.18 newtons for how we're going to be using it here in just a little bit. Okay, so, and that kind of makes sense. And remember our measurement, it was 7.2, and our calculation 7.18. That's almost spot on. And then our measurement over here was 3.8, and this is 3.74, so those are very good. Okay, so what we need to do now is kind of combine all of this. This is essentially the equilibrium rule. And so we'll find some open space. We'll do it right over here in this section. The equilibrium rule, it says when something's not moving, and our spring scales were not moving, the sum of all of the forces in the x direction should add to 0. The sum of all the forces in the y direction should add to 0. So let's do the ones in the x direction. Let's do those. We'll do the ones in the x direction right over here. So here's how we would write this equation. We would use this big sigma. Sigma fx is equal to f1x plus f2x plus f3x. F1x is this value over here. Remember, we did not have to break this one up into components. It's negative 4.3 newtons. F2x is this little leg right here, and that was 0.69, positive 0.69 newtons. And F3x is this leg down here at a positive 3.74 newtons. So we add those up, we've got a negative 4.3 and a 0.69 and a 3.74, and that gives us a positive 0.13 newtons. Now it's supposed to add to 0, and that's not too bad. That's about 0. So, you know, I'm not too disappointed with that. Let's do the y, and what's going on in the y direction. We'll do that one, well, let's just tuck it in here so that we're, you know, kind of consistent, looking in the same place. So summation of the forces in the y direction is going to be F1y plus F2y plus F3y. Now F1y is over here. There was no y component to this, so that's 0. F2y is this leg right here at a positive 6.56. And F3y was this one down here, negative 7.18 newtons. So we have 6.56 minus 7.18. It's a negative 0.62 newtons, negative. So this one's a little bit further off. This is not quite equal to 0, so that one could be better. But you know, not terrible. I think overall that turned out all right as well. So anyway, so that is the component method.